Let's talk about loose dot structures and the octet rule. So remember, row 1, elements. Basically, we're talking about hydrogen. They only have one bond. So only up to 2 electrons. Why is that? Because remember, it only has an s orbital. When you look at row 2, you have only up to an octet. So we have basically our metals. So let's see, we have lithium, beryllium, boron. These are less than an octet. Right? This is because they have less than 4 valence electrons. If we look at carbon, nitrogen, oxygen, fluorine, and neon, you get up to an octet. Okay? When we get to row 3 or more, then they prefer an octet. But you can expand if necessary. Okay? And then we also have complex molecules. With multiple central atoms. Okay? And once we draw them, we're then going to start talking about molecular geometry. This is they'll be part and parcel with what we're doing. Okay? So let's first do an example where we're doing a row 2. So let's do your ozone. Okay, so ozone. So since all of my atoms are the same, I'll have one as my central atom. You surround it with the other 2. Say, okay, and how many electrons does ozone have? Ozone has 3 times 6. Remember the group number 6A? Valence electrons. We have 18 valence electrons to work with. Okay, so central atom for my single bonds. Let's do my octet. Then my lone pair. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've used up all of my lone pairs. But if you now look at each atom, this has an octet, that has an octet, 2, 4, 6. This only has 6 electrons. So what you need to do is, since I have too few, I need to share electrons by using multiple bonds. So now we're going to have to look at a double bond or triple bond. Okay, so what we'll do is let's take these 2 electrons and share it between the 2 oxygens. If I do that, this is what my structure now looks like. I'm not going to touch this one because that one I didn't do anything with. Add lone pair here, lone pair here. These 2 electrons became this bond. Have a lone pair here, I have my lone pairs here. Okay, so now that we have ozone, let's go through. Double check my octets. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. So my octet rule is satisfied. And now what we need to do is then talk about formal charges. So remember, formal charges basically are my group number minus the lines minus the dots. Okay, so 6 minus 1, 2, 3, 4 minus 2. So that's 0. So we don't write anything. This one, I have 6 minus 3 minus 2. So that's a plus on that oxygen. Okay, it's not an ion, it's a formal charge. It's just to kind of keep track of where all our electrons are being distributed. This one is 6 minus 1, 2, 3, 4, 5, 6, 7, which means this is a minus. So what's nice is that ozone, even though it's a neutral molecule, it does have formal charges. And the formal charges add, okay, remember, the formal charges, you add them together, add to, when you sum, let me just rewrite this. When you sum of the formal charges is equal to the charge on the molecule. So if it's an ion, it'll be the charge of the ion. If it's a molecule, it is basically the charge of the molecule. In this case, it sums to 0. So that's how we look at coming up with ozone. Follows the octet rule, we did our formal charges. Now before we erase this and move on to the next one, let's look at my central atom here. It has 1, 2, 3 electron groups. So it's not linear with 3 electron groups. The electron group geometry is going to be trigonal planar. Okay, so let me erase the board and redraw it, and then we can also talk about our molecular geometry. So ozone, we said, was trigonal planar for the electron group geometry. It's trigonal planar. Okay, and what it looks like then is like that. Okay, now if we look at the molecular geometry, I do not include the molecular geometry, any of the electrons, the lone pair electrons. I'm only looking at the atoms. Okay, so when I have one lone pair, instead of trigonal planar, look at it, looks bent. And so that's what we call it for our molecular geometry. And last but not least, and this is a really important concept, so I'll use it on this one, it's called resonance. At resonance, it looks like all you're doing is drawing loose thought structures, but the key is you're going to basically hold down the atoms. And you're going to look at how the bonds, how the electrons can redistribute. Okay, so I'm going to call this atom 1, atom 2, and atom 3. Okay, so when I redraw this, atom 1, atom 2, and atom 3, they're in the same orientation. Okay. But what I can do is I can actually take these electrons, and I can form a double bond here. And these electrons have to move away in order to make sure that my oxygen only has an octet around it. When you do that, let's see what happens. Here are my lone pairs I haven't touched. I haven't touched this one. Okay. And these lone pairs I didn't touch. So let's follow the arrows. Now my arrows say these electrons become a bond, and this bond becomes a lone pair of electrons. Okay, so when I indicate resonance forms, or resonance structures, all I'm doing is moving the electrons. Okay, so I use a double-headed single arrow here, and then we'll recalculate the formal charges. And that's what it looks like. Okay, so before we move on to the exceptions, all right, let's go through this. So from what can we learn? So from one structure, so one, you have a molecular formula. And then you make a loose dot structure. Okay, and when you make your loose dot structure for your compound, what can we learn? One, you have your formal charges. So charge distribution. Two, we looked at resonance. Okay, resonance can only occur if you have distribution of electrons, right? Can only occur if the atoms have lone pair electrons or multiple bonds. Or rare, but we do see it, where you have like a single electron in a radical. Okay, what else did we learn about just from a single molecular formula? And we drew the structure. Formal charges, resonance, then we knew about our electron groups and electron group geometry. We can get the molecular geometry. And we didn't talk about it for ozone because ozone didn't have any. We can talk about molecular polarity. So this is all we can get from the molecular formula and get a structure. Then this is all the information you can actually get from a single structure. All right, let's do 2 more examples. Okay, so the second example that we're going to do is an expanded octet. So if we talk about exceptions, we have the radicals have an odd number of electrons. So when you calculate that, you say, well, what do I do with my odd one? Instead of having a lone pair, you're going to have a lone single electron. You can have less than an octet. But the one that you'll encounter the most, that's an exception, is an expanded octet. And remember, this is for central atoms that are in row 3 or greater. Okay, so let's do something like your phosphate ion. So remember, for ions, if you have a negative charge, for every negative charge you add an electron. So I have 5 plus 4 times 6 plus 3 gives me 27, 32 valence electrons. Okay, the least electronegative atom, which is phosphorus, goes in the center. I'm going to surround it by my other atoms. 2, 3, 4. Okay, draw my single bonds. 2, 3, 4. That's 8, so that gives me 24 left. So you're going to put it here. Okay, so now I have my 32. Now let's take a look and calculate my formal charges. That's a minus, that's a minus, that's a minus, that's a minus, and this is a plus. Well, that's a lot of formal charges. And I have a minus right next to a plus. So what we can do, we say I have a minus next to a plus, and phosphorus is actually in row 4, right? So basically I can expand it, right? Is it row 4? No, row 3. So I can expand it. It's in row 3. So we're going to expand phosphorus. Okay, and the way I'm going to do that, I'm going to take this lone pair and I'm going to share it between my phosphorus and oxygen. Now, let me just redrop in black and put in blue what I've done. Here's my phosphorus. Okay, here's the oxygen. Okay, and I say I take these 2 electrons and I form a bond right here. So let's calculate the formal charges. 6 minus 6, nothing here. That's a minus, minus, minus. Then in phosphorus it's 5 minus 5. So now I went from 5 formal charges to 3. So this is a better or more preferred structure. Okay, so let me just make a little space here. Okay. All right, so Now that we know this, we can draw a set of resonance forms for this, and we can draw this in the correct geometry. So let me go ahead and erase this, and we'll focus on my phosphate ion. So what I had drawn was phosphate, like that. I have 1, 2, 3, 4 electron groups. Okay, because of that, we know this is tetrahedral. And since I have 0 lone pairs on my central atoms, my molecular geometry is also tetrahedral. Now when you draw this, you have to draw it so it looks tetrahedral. Right now it's all flat on the board. So what we do is we use solid and dashed wedge bonds. So when it's tetrahedral, we know that the bond here must be 109.5 degrees. Okay? So how do I show that these are three-dimensional? When it's coming out of the plane towards you, you use a solid wedge bond. If it's going away from you into the board, use a dash wedge bond. And if you want, you can use toothpicks and marshmallows and then make the structure. So you're trying to draw it as 109.5, and then you make this three-dimensional that way. Okay? Now, what happens if I say, well, I'll show you an example of a resonance forms, and you can do the rest. Suppose instead I say, well, what's a resonance form? Well, if I take these two, hold all my atoms now still, and say, what happens if I form a bond here? Then this gets kicked out. So my resonance form, 1, you'll have a total of 4, okay, that all look like this. You would see something like this. That's probably wedge bond. Okay, so this is a resonance form. Okay, let's just, before you can continue to draw a resonance form. It'll be 1, 2, and a third one that has more formal charges. Okay, so you'll have more resonance forms. Let's just talk very quickly about polarity. That is this a polar or a non-polar bond? And if you think that this is a polar bond and it's always pulling towards the oxygen, then basically it's vector addition. And since these are all of equal magnitude and it's symmetrical, so they're all pulling away from each other, even though I have polar bonds, so you can double check on your electronegativity. You're going to look at the difference in electronegativity. Okay, it's going to be between 0.4 and 2.0. Okay, the symmetry of the molecule this indicates it is, and this is symmetry, is 3D symmetry, not just 2D. So the 3D symmetry, this is a non-polar, okay, structure. Okay, so there's no permanent dipole to this. All right, so that's how we take a look at the polarity. Okay, now, so we actually can, from a single structure, think about all the different pieces of information that you can get just by looking at your single structure. Okay, let's take a look at something like sulfur hexafluoride. Okay, so sulfur hexafluoride, that's 6 valence electrons plus 4 times 7. That gives me about 34 valence electrons to work with. The sulfur is my central, and move it over here to the left. Okay, my sulfur is my central atom surrounded by my fluorines. Drawing my single bonds, 2, 4, 6, 8. Then put your octets on the surrounding ones. If they were hydrogens, you don't, because the single bond completes their orbital configuration. Whereas anything row 2 should be an octet. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 2 more, so I put them right here on the central atom. Okay, no sharing, I had extras this time. Okay, so now that I put them on the central atom, let's take a look. How many electron groups do I have? 1, 2, 3, 4, 5. I have 5 electron groups, which means my electron group geometry is trigonal bipyramidal. Okay, I have 1 lone pair. That means my molecular geometry is seesaw. So let's take a quick look at this. When we're looking at trigonal bipyramidal lone pairs, always go on the equatorial plane. Okay, so I'm going to give you 2 drawings. Okay, this is my lone pair on the equatorial plane. We draw that one first, and I'll do the lone pair in pink on the axial plane. All right, so let's take a look on the equatorial plane. Here is my sulfur, and I have the axial plane, and then I have my equatorial plane. Okay, if I put my lone pair on the equatorial plane, and my fluorines here, 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 okay, I have 2 90-degree interactions. Okay, so it's going to push against 2. Suppose I put it on the axial plane. Here I have 1, 2,